Hello guys, my name is IBM and I would like to take you through the October-November 2024 papers. One of my students has been asking me to record these papers, so today I decided to come and record the papers, the October-November 2024. And I'm going to start with paper 2-1 because many students want the AS papers, so I'll start with the paper 2-1. But before I start recording the paper 2-1 of October-November, I would like to introduce to you our website, which is www.caieresourcemaster.com, which is going to be the home to all our resources. We realized we can't keep our resources on the Google Drive. It would get full and it was really stressful. So we decided to come up with a website where I am one of the contributors to the physics department. So I request you to go and visit our website www.caieresourcemaster.com. When you go to the website, it looks like this. And on the website, you can find tutorials. If you have a brother sibling doing IGCSE, you'll find things to do with IGCSE. But since I'm dealing with AS physics, on our website, when you go to AS, you'll find specifically I selected physics. You'll find a folder for tutorials where you find the topics of AS, the syllabus and all the topics. Unfortunately, these are not free because the teacher put in a lot of effort to come up with these with these uh, with these with these materials. So these may not really be very free, but you can find them there. For those who are willing to purchase them, you can always purchase them. Of course, purchasing would require using PayPal. So I can also show you how to purchase from this website. If you go to topical questions, these ones have been solved in the YouTube videos, especially for physics. So you can find all the topics that you want under topical questions. All the topics, they are relatively cheap. So for example, if you decide to purchase, let's say, errors and uncertainties, you just click on it and add it to cart. You may want to purchase other documents. You can go on adding so that you purchase them at once. So this is errors and uncertainties, and you try to purchase. You enter your first name, your last name, and your email address. Then you select PayPal, checkout. So then it will ask you to enter your details, your card number. You enter the card number and then you proceed with the payments. Once the payment is complete, the purchase page will look like this. Once the payment is complete, since you have finished to purchase, you will see the download part, the download link, where you just click and download the document which you have purchased. So that is basically how this website works. You pay using PayPal, where you enter your details, and then you will just get the page will now look like this after you complete the purchase. And then after completing the purchase, you can just click download and download your document, as simple as that. Okay, so those who want to support our website, you can go and create a free account. It's totally free. You can download the past papers from this. For example, the papers I'm going to record can be found in the folder for past papers. You can just come to our website, look for the folder for past papers, and then check out the papers. For example, the October-November 2024 papers, I think they're the ones on top. And the one I'm going to record is paper 2-1, which you can find there. If you want to verify with the answers, the mark schemes are also at the bottom there. You can always check and try to verify. The role of the video I'm going to record is just to explain the solutions in more details where possible. Okay, so let's go to the question paper. This is the October 2024 paper, and this is paper 2, AS level structured questions, and this is component 2-1. I will not go into the instructions. I will not go through the given data. I will go straight to question number 1. Define density. So you can define density as simply mass divided by volume, or mass per unit volume. The figure shows a cuboidal glass block. A student measures the mass m of the block and the side lengths x, y, and z. So this is a cuboid, so the volume of the cuboid is going to be x times y times z. So these are the measurements. We have mass, we have x, y, and z. Determine the density of the cube. Of course, we know that density is mass over volume. That's where we started from. So we just substitute in the formula. Density is mass over volume. So I'll say density is the mass divided by the volume, which is the same as the mass divided by the volume, which is x, y, z. So when I substitute, I think the mass was the mass is 0.243. So I'll say 0.243 divided by the dimensions. We have 5.41, but this is in centimeters, 11.09 in centimeters, 1.62 in centimeters. So because we want answers in the answer in kilograms per meters cubed, I'm going to change all of them to meters squared. So centimeters to meters will be times 10 to the power of minus 2. So each of them I'm going to multiply it by 10 to the power of minus 2. So this is going to be 5.41 times 10 to the power of minus 2, then times 11.09 times 10 to the power of minus 2, then times that is 1.62 times 10 to the power of minus 2. Let me check to see if I maintain them. Okay. So I'll just now press my calculator. Starting with the denominator, I have 0.0541 times 0. I think that is 1109 times 0.0162. Then I'll say 0.243 divided by the answer, which is giving us 2,500. So the density is 2,500 kilograms per meters cubed. Calculate the percentage uncertainty in the density. So we have already seen that density is equal to the mass divided by x, y, z. So this means if I consider the fraction uncertainties, then the fraction uncertainty in the density should be equal to the fraction uncertainty in the mass sorry about my pen. Fraction uncertainty in the mass plus fraction uncertainty in x plus fraction uncertainty in y plus fraction uncertainty in z. So if I want to find a percentage, I multiply both sides by 100. So I'll simply say percentage uncertainty, the density is going to be for mass. I think the uncertainty in mass 0.001, 0.010101. Okay. So this is going to be 0.001 divided by 0.243, then plus 0.01 divided by 5.41, then plus 0.01 divided by 11.09, then plus 0.01 divided by 1.62. I'll multiply this by 100% to change it to a percentage. Now here I don't consider the units because I'm dividing. The absolute uncertainties have the same units as the true value or as the most likely value. So the units cancel out. I don't need to add the power of 10 here because it will be a wastage of time. So I'll solve this with my calculator. So I have 0.001 divided by 0.243 plus 0.01 divided by 5.41 plus 0.01 divided by 11.09, then plus 0.01 divided by 1.62. Then I multiply this by 100, which gives us 1.3%. So the answer here is going to be 1.3%. Then suggest one possible cause of the true value of the density of the glass is different from the answer in B Roman because of a systematic error. So there are two causes of a systematic error in an instrument. The instruments which are considered here is we are measuring mass. Mass is measured using a balance. Then these lengths, when we look at the order of these lengths, the lengths are very small. So we can say 5.41 centimeters. This could be measured using a vernier caliper. So these ones are measured using the calipers or the vernier caliper. So if there's a systematic error, then there is a zero error in the balance or a zero error in the caliper, or the balance is wrongly calibrated or the caliper is wrongly calibrated, because those are the two systematic errors. So this question was suggest one possible cause of systematic error. So I'll say zero error. It could be caused by zero error on the vernier calipers or the calipers, or I can say zero error on the balance which has been used to measure the mass. That's number one. Number two, I can say wrong calibration of the calipers. Wrong calibration of the vernier calipers, or I can say wrong calibration of the balance. Those could be some of the possible causes of systematic error, which has made the answer to be different. Define linear momentum. Of course, we know that momentum is mass times velocity, so it's just simply say mass times velocity, or you can say product of mass and velocity. Normally, when they put the word linear here, people think it's something different. It's just the product of mass and velocity, that is linear momentum. A car of 1,800 kilograms is moving in a straight line. The figure shows the variation with the time t of the momentum p of the car. So this is momentum against time. Calculate the maximum speed reached by the car. Maximum speed. We know that momentum is mass times velocity. So it means maximum speed v equals to p over m. So if v is maximum, the momentum must also be maximum. So this is going to be maximum momentum divided by the mass. So this is going to be, we look for the maximum momentum from the graph, and this is, I think this is 7.2. So that's 7.2 times 10 to the power of 4. Then we divide by the mass, which is 1,800. And when we check this with our calculator, 7.2 exponent 4, divide this by 1,800, that is 40. So the speed here is going to be 40 meters per second. Then calculate the maximum kinetic energy of the car. Of course, you must write the formula for kinetic energy as being equal to a half mv squared. When I make a substitution, this is going to be a half times 1800 times the speed, which is 40, but this is squared. So this gives us half is 0.5 times 1800 times 40 squared. So that is 1,440,000 joules. 1 million. So I can write 1.44 times 10 to the power of, those are 6 times 10 to the power of 6. I have to erase this. Okay, so that is the maximum kinetic energy. Show that the acceleration of the car at t equals to 4 is 5 meters per second. So t equals to 4 is here, and this is a straight line. And remember, this is a graph of momentum against time. So we know that the resultant force equals to the mass times acceleration, which is the same as the rate of change of momentum. So resultant force is the rate of change of momentum. That means the acceleration is going to be equal to, of course, change in momentum over change in time, that is the gradient. So the acceleration is going to be the change in momentum over time, then divided by the mass, which could be the same as the gradient divided by the mass. So the acceleration can also be the gradient divided by the mass. Therefore, I will simply say the acceleration is going to be the gradient. I'll just take at 4, but even if I take 7.2, so if I take at 4, I think this is 3.6. So it is 3.6 minus 0 over 4 minus 0. That would be the gradient. So this is going to be 3.6 times 10 to the power of, it is power 4 minus 0 divided by 4 minus 0. Then this is going to be divided by the mass, which was 1,800. And when I press my calculator, 3.6 exponent 4 divided by 4 divided by 1,800. Sorry, 3.6 exponent 4 divided by 4 divided by 1,800. That is 5. So this is 5.0 meters per second squared as required. Then determine the distance traveled by the car between times t equals to 0 and time t equals to 12. We want distance. Now I want you to notice that this is a graph of momentum against time. And we know that the speed v equals to the momentum divided by the mass. If we had a distance time graph, the distance would be equal to the speed times time. The distance would be equal to the speed times time, or which would be equal to the area under the graph of velocity against time. Now this time we have a graph of momentum against time. So it means the distance is going to be where there is v. I'm going to be putting there momentum divided by mass times time, which means since we have a graph of momentum against time, product of P and T is going to be the area. So the distance is going to be equal to the area divided by the mass. So the distance is going to be the area under the graph divided by the mass. Okay. So the distance is going to be equal to the area under the graph. Divide this by the mass. The graph is a triangle, so I'll just use a simple formula for the area of a triangle. So that will be a half. The base was 12, and the height is 7.2 times 10 to the power of 4. Then I divide this by the mass, and the mass was 1800. So that is going to be the distance traveled by the car in that total time. You can find the area different in other using a different method, dividing it into two triangles, but even using one triangle is fine. So this is going to be 0.5, a half, times 12, times 7.2 exponent 4 divided by 1800, which is giving us 240 meters. On the figure, sketch the variation with the time of the acceleration A of the car in B from t equals to 0 to t equals to 12. Let's look for the acceleration here. Remember, for the first part, for the first 4 seconds, the acceleration is 5 meters per second. And notice that it's a straight line, so the acceleration is going to continue up to 8. Because it's a straight line, the acceleration here is the same acceleration here. So for the first 8 seconds, it is a straight line, the acceleration is constant because the velocity is increasing uniformly since the velocity is directly proportional to momentum. So for the first part, the acceleration is constant and it is 5. It remains 5, which we have calculated in part 3. For the first 8 seconds, it still remains 5 meters per second. Then for the next part, for after 8 seconds, they said sketch the variation with the time t of the acceleration A of in B from t equals to 0 to t equals to 12. Let's find the acceleration. Of course, we said acceleration. Let me say from t equals to 0 to t equals to 8 seconds. Acceleration was 5 meters per second squared. Then from t equals to 8 to t equals to 12, the acceleration must be equal to the gradient divided by the mass. And the gradient is going to be 7.2 times 10 to the power of power 4 minus 0 divided by the time from the graph. The time is 12 minus 8. That is the gradient. Then we divide this by the mass as we did in part 3. So divide by the mass, which is 1800. And from my calculator, I have 7.2 exponent 4. Divide this by 12 minus 8, which is 4. Divide this by 18, which is 10. But I want you to remember that this acceleration is negative because the final velocity is 0 from the graph here. The final velocity is 0 because the final momentum is 0 here. The initial velocity, we are starting with 7.2. So I would have put this as 0 minus. I would have done this as 0 minus. Let me change this. So here the acceleration is going to be 0 minus 7.2 times 10 to the power of 4 divided by 4 or divided by 12 minus 8. This is the gradient. Then divide by the gradient by the mass as we did in part 3. So this gives us negative 10 meters per second squared. So get your ruler, draw a horizontal line along 5 using a ruler. This is the initial acceleration remains constant. Then now draw another line at the bottom here. Let me try to increase the thickness. Then I'll just draw a step here. So you can use a ruler and draw something very beautiful. Maybe whenever I draw rough work, students are not don't always want to improve their work. So I'll use a ruler also. Okay, so that will be the graph. Initially, the acceleration is constant for the first 8 seconds and is 5 meters per second squared. And then for the last 4 seconds is negative 10 meters per second squared. Okay, so let's see question number 3. State what is meant by work done. Of course, we know work done is force times displacement in the direction of the force. So this is a product of force and displacement in the direction of the force. So the displacement must be in the direction of the force when you are defining work done. A block of mass m is raised vertically at a constant speed. That means there is no change in kinetic energy. The acceleration is 0. The vertical height gained by the block is delta h as shown. Derive an expression in terms of m and delta h for the change in gravitational potential energy, delta EP of the block. State the meaning of any other symbols you use. So first of all, we said work done is force times displacement. Work done equals to the force times the displacement, as we mentioned earlier on. But then the force is going to be equal to the weight because we are trying to overcome the weight. So the force is going to be equal to the weight, which weight is going to be equal to m times g. And g is the acceleration of free fall or acceleration due to gravity. Acceleration of free fall. Therefore, and of course the displacement is delta h. So the work done is going to be the force, which is mg, times the displacement, which is going to be delta h. However, I want you to notice that the work done by the repelling force is the change or the gain in gravitational potential energy. So the work done by the lifting force is equal to the gain or the change in gravitational potential energy. Hence, it implies that the change in gravitational potential energy is simply going to be mg delta h. So that is the expression for the gravitational potential energy. An electric motor has an input power of 900 watts. The motor takes 1.0 minute to lift a load of weight 240 newtons at a constant speed. The speed is constant. Through a vertical height of 150 meters. Resistive forces are negligible. Show that the work done by the motor on the load in 1 minute is 36 kilojoules. So we have already said the work done is equal to the force times the displacement. And when we make substitution, the force we are overcoming here is the weight, which is going to be 240. The displacement we are going to move through is the vertical displacement, which is 150. And I think when you multiply this, could be giving you 36,000 joules, which is actually 36 kilojoules. I can check this. 240 times 150, that is 36,000. Then determine the useful output power of the motor. The useful output power. We know that power is equal to the rate of doing work, which is the work done, divided by the time taken. So when I make substitution, the power is going to be the work done, which is 36,000. And I think the time was 1 minute. 1 minute is 60 seconds. So I think this is automatically 600. So this is going to be 600 watts. Then use your answer in C Roman 2 to determine the efficiency of the motor. Of course, we know that efficiency equals the useful power output over the total power input. So efficiency equals to the useful power output divided by the total power input. Of course, if we want as a percentage, we may multiply by 100, but it is not necessary. So the useful power output is 600. Then the power input, what was the power input? The power input was 900. So we divide this by 900. So it is 600 divided by 900. And let me check with the calculator. 600 divided by 900. That is 0.6 recurring, which is 0.66667, which is approximately 0.67. Some of the power wasted in the motor is dissipated by the resistor of its coil, by the resistance of its coil. This dissipated power is 280 watts. The coil of the motor is made from wire of total length 23 meters. The wire has cross-sectional area 2.6 times 10 to the power of minus 8 meters squared and is made from a metal of resistivity 1.7 times 10 to the power of minus 8 ohm meters. Calculate the current in the coil. So we want to find the current in the coil. We know that resistance equals to rho L over cross-sectional area. We have rho, we have cross-sectional area, we have the length. So it means we can find the resistance. And we know that power since they have given us the power wasted, we know that power wasted or power dissipated is equal to I squared times R. which therefore means when I combine these two equations, it means that our power is going to be I squared times rho times L divided by area. When I make I the subject, I is going to be the square root of power times the area divided by rho times L. Okay, so it means the current in the coil is going to be the square root of the power, which is 280, cross-sectional area, which is 2.6 times 10 to the power of minus 8, divided by resistivity, which is 1.7 times 10 to the power of minus 8, then times the length, which is 23. So I'll check the calculator. 280 times 2.6 exponent minus 8, I know that one cancels, divide by 23 times 1.7 exponent minus 8. Then we find the square root of the answer, which is 4.3. So the current is approximately 4.3. Okay, so that is going to be the current. So define the Young modulus of a material. We know that Young modulus equals to stress divided by strain. So I'll simply say Young modulus is stress divided by strain. The ratio of stress over strain, that's Young modulus. A metal wire P obeys Hooke's law. That obeys Hooke's law is stretched within the limits of proportionality. That means it's just a straight line. Force is directly proportional to extension if the limit of proportionality is not exceeded. On the figure, sketch the variation of the tensile force F in the wire with its extension X. Because the limit of proportionality is not exceeded, then this is just a straight line from the origin, or a straight line through the origin. So I'll just draw a straight line through the origin. It is just a straight line through the origin. So just use a ruler and draw a straight line through the origin, because force is directly proportional to extension if the limit of proportionality is not exceeded, so it will be just a straight line through the origin. Set the name of the quantity represented by the gradient. So we know that F equals to K times X, and the gradient K, the gradient is going to be the K, which is the spring constant. So this is going to be spring constant. Then state the name of the quantity represented by the area under the graph. The area under the graph will be equal to a half, because it's a triangle. It is going to be a half times the base, which is going to be x times f. So it is a half f x, and the area of the triangle, and the area is actually equal to the elastic potential energy. So this is the elastic potential energy. It's the elastic potential energy which is stored in the wire. Another wire Q is made from a metal that has twice the Young modulus of the metal wire P. So if the Young modulus of P is E, then the Young modulus of Q should be twice E. Wire Q has the same volume, so they have the same volume. And if they have the same volume, volume of wire P is the same as volume of wire Q, and volume is cross-sectional area times length. So it means the area of wire P times the length of wire P, which I'm going to call LP, should be equal to the area of wire Q times the length of wire Q, which is LQ. Wire Q has the same volume as wire P, but has double the cross-sectional area of a wire P. So the area of wire Q is twice the area of wire P. So I will say where there is area of wire P, wire Q has the same volume as wire P, but it has twice the cross-sectional area. So if the area of P is A, the area of Q should be twice A. So I will say A times length of P is going to be twice A times length of Q. What does that imply? It implies that the length of Q is half the length of P. When I simplify this equation, it means that the length of Q is equal to half of the length of P. Okay, the two wires are extended by equal tensile forces, so F is the same within the limits of proportionality. State and explain how the extension of wire Q compares with the extension of wire P. Okay, I'll just try to evaluate the extension somewhere here at the bottom, even though it is, if you're a good mathematician, it may not be necessary. So let's start with wire P. For wire P, its Young modulus is going to be E. This is going to be called the tensile force F. Its original length, let the original length of wire P be L naught. Divide by its cross-sectional area, we said it is A. And its extension, I'm going to call it EP. Then for wire, this was for P. Then for Q, its Young modulus was twice E. Its the force tensile force was the same. The length of wire Q was half wire P. So this is going to be times half of L naught. If P is L naught, then Q is L naught over 2. Divide by the area was twice. So I'll say twice A. Then times the extension, which is E for Q. When I divide these two equations, Q divided by P, I'll have that twice E divided by E equals 2. Most of these cancel out. So I have, let's say I have F L naught divided by 2 divided by twice A EQ times, I'll get the reciprocal of P, which is A E P divided by F L naught. So I want us to be able to see that A has cancelled, F and L naught have also cancelled, and E has cancelled. So people should be able to see that we have remained, the 2 goes the other side, so it becomes 4 equals to, there's a 2 which goes in the bottom, so it becomes E P divided by twice E Q. This 2 again goes the other side, so it means the extension of wire P is going to be 8 times the extension of wire Q. Alternatively, the extension of wire Q is equal to 1 over 8, the extension of wire P. Okay, I all do this just to show you, but I could have done this. I could have written the answer without any explanation. So I will simply say that the length of Q, starting from this part here, the length of Q is half length of P. That's number 1. Number 2, extension. We have seen that we know that extension is directly proportional to length. From this equation, you notice that extension is always directly proportional to length. So extension is directly proportional to length. Extension is proportional to length. And inversely, I think it is also inversely proportional to the area. and inversely proportional. Extension is directly proportional to length and inversely proportional to area. And of course, we have seen Young modulus. Oh, I can just say and extension is proportional to length. From this formula, extension, when I make E the subject, E is going to be equal to F L naught divided by E and A. Okay, so extension is proportional to length and inversely proportional to area and Young modulus. And Young modulus. So you can see this formula here when I make small e the subject. So it means extension of Q is going to be 1/8 because it is inversely proportional to area and also inversely proportional to the Young modulus. Yet the Young modulus is twice. The area is also twice. That makes it power 4. But extension is proportional to length. Okay. And yet we have seen that the length of Q is a half. So it is a half times 1/2 times 1/2. So extension of Q is equal to 1/8 times the extension of P. Or I would say the extension of P is 8 times the extension of Q. It's the same thing. Potassium 40 undergoes a beta minus decay. Remember, beta minus is 0, -1. To form a nuclide of element X, particle Z is emitted during the decay. The equation for the decay is shown here. State the values of P, Q, R, and S. So we know that beta is 0, -1. So R is 0 and S is -1. Then, of course, during beta decay, it is accompanied by Z. Because beta minus is an electron, it is accompanied by an anti-electron. So this one is going to be an anti-electron. Not anti-electron, anti-neutrino, not anti-electron, anti-neutrino. So that is going to be an anti-neutrino because a particle is accompanied by an anti-particle. Then state the value of PQ. So balancing the nuclear number, this remains 40. Because this is -1, this should be 20. So that's 20 plus -1 is 19. So this is going to be 40 and this is going to be 20. And we have said that the particle is the or you can say the electron neutrino. It is called the electron antineutrino. Okay. The electron antineutrino. State the name of the class of fundamental particle to which both beta minus particle and Z belong. So the beta minus particle or the beta particles and the antineutrino, these ones are leptons. They are not made up of quarks. Determine the quark composition of an alpha particle. So that an alpha particle is a helium nucleus which has 2 protons plus 2 neutrons. The proton has up, down, and we know that the neutron the neutron has up, down, down. So 2 protons plus 2 neutrons will be equal to 2 into up, up, down, plus 2 into up, down, down, which is going to be 4 up, 2 down, plus 2 up and 4 down. When you sum up the ups, you get 6 up and you'll get 6 down. So the quark composition is going to be 6 up and 6 down. So an alpha particle has 6 up and 6 down. Two coherent sources X and Y of microwaves of frequency 2.5 times 10 to the power of 10 Hz are a distance of 0.18 meters apart in a vacuum as shown in the figure. There is a phase difference of 90 degrees between the waves emitted at the two sources. Now, if the waves emitted from the two sources have a phase difference, then we cannot form a maximum at the center. If the phase difference is 180 at the center, it would be a minimum. But now that it is not 180, it is instead a 90 at the center, it is also not a minimum. If the phase difference was 0 at the center, O is a point which is at the center between the two sources, you see it is along the center line. If the phase difference between X and Y was 0, we would expect a maximum at O. If the phase difference between X and Y was 180, where there is a maximum, we expected a maximum when the phase difference was 0, it would be a minimum. But since the phase difference is 90, we even don't expect a minimum at all. We would expect it either below or above. So there is a phase difference of 90 degrees between the waves emitted at the two sources. A microwave detector moves along line PQ, which is parallel to the line joining the two sources and 2.3 meters away from it. Point O is on the line PQ at a position that is equidistant from the two sources. So O is the center. Point A is the position of the line PQ where the intensity of the microwave is the greatest. So at A we have a maximum. We have a maximum at A when the phase difference, remember, between the two sources is 90. Explain why the position of greatest intensity is not at point O. In other words, explain why we don't have a maximum at point O. Of course, we have already seen the phase difference of 90 at the source means that there is going to be a phase difference of 90 at point O, and the phase difference of 90 at point O cannot cause a maximum. So we can say the phase difference of 90 degrees at the source or at the sources means that the waves are not in phase at all. If the phase difference between the two sources was 0, the waves would arrive at O with a phase difference of 0. If the phase difference between the two sources was 180, the waves would arrive at O with a phase difference of 180. If the phase difference between the two sources is 90, the waves are arriving at O with a phase difference of 90. And the phase difference of 90 does not result into an intensity maximum, does not result into the greatest intensity. So the phase difference of 90 degrees at the source means that the waves are not in phase at all. They have a phase difference which is not 0 or which is not 360. Yet, for maximum intensity, the waves must be in phase at the at the point of detection. But for maximum intensity, or for greatest intensity, the waves must be in phase at the point of detection. Okay, on the figure, draw a cross to show the position of the point on the line PQ where the intensity minimum, that is the closest to point O, occurs. Of course, if we have a maximum at A, most likely the phase difference here it could be 0. And if at O, the phase difference between the waves is 90, then of course I must add 90 onto this so that the phase difference becomes 180 to have a minimum. So it means if the phase difference at A is 0, that's where we have a maximum, and at O, the phase difference was 90. For us to have a minimum, then the phase difference between the maximum and the minimum is 180 degrees. So where it means on this we add 90. So we are going to mark the point at 90 degrees. Another point where the phase difference is 180 degrees, that is from A to that point, the phase difference will be 180 degrees between A and that point, and that point will be equidistant from O. The distance between O and A will be the same as the distance between O and that point, and I'll label this point B. So I'll try to rub off some of these marks so that I can draw a clear diagram. So this distance is approximately, let me try to measure so that I try to be very accurate. So the distance between O and A is about 0.8. Okay, so this is going to be B somewhere here. I'll label that B. So between A and B, the phase difference is 180 degrees, and that means there will be a minimum at point B. Then show that the wavelength of the microwave is 0.012 meters. So wavelength. Of course, from the general wave equation, V equals to lambda times F. So the wavelength is going to be, because it was a microwave, V is 3 times 10 to the power of 8, divided by the frequency. Show that the wavelength is that. The frequency, what is the frequency? The frequency is 2.5 times 10 to the power of 10. So divide by 2.5 times 10 to the power of 10. I'll just press my calculator. 3 exponent 8 divide by 2.5 exponent 10. So that is 0.012 as required. For point A on line PQ, determine the difference in distances delta x traveled by the microwaves from X and the microwaves from Y. So note that at A we have a maximum. At A we have a maximum, and at O we have a minimum. Remember, the waves had a phase difference of 90 degrees from the source. So if they had a phase difference of 90 degrees from the source, then and yet they are forming a maximum at point A, then I have to consider the phase difference. Of course, the distance out of step must now compensate. So the phase difference is equal to 360 into the path difference, which I'm going to call delta x, divided by the wavelength. Of course, this will be in degrees. So the phase difference between the waves was 90 degrees. And because it was 90 degrees, then if they arrive in phase, then one wave must have been traveling a longer distance than the other. So there must be a path difference for them to be able to arrive in phase. But if they travel the same distance, yet the phase difference between the source was 90, they must arrive with the same phase difference of 90. But if they don't travel the same distance, then they can form a minimum or a maximum. So this is going to be equal to 360 degrees, of course, into delta x divided by the wavelength, which was given as 0.12. So making delta x the subject, so delta x is going to be equal to 90 divided by 360 times 0.12. So delta x is actually 0.012. Let me try to check this. So that is 0.012. Ninety divided by 360, that is a quarter times 0.012, which is, divide this by 4, that is 3 times 10 to the power of minus 3 meters, or I can write 0.0030. I want to write two significant figures. I try to always write more significant figures. 3.0 times 10 to the power of minus 3. Use the formula of the double slit interference of light to calculate the distance between the adjacent intensity maxima on line P, that is small letter x. We know that for a double slit, lambda equals to AX divided by D. So x is the distance between the successive minimum, is going to be lambda D divided by A. We just make a substitution. The wavelength is 0.012. Divided by, times D, which D was, I think, 2.3. Then divide by 0. I think A was 0.18. From my calculator, 0.012 times 2.3 divided by 0.18. That is 0.15. So this is going to be 0.153 recurring, or approximately 0.15. Lastly, I think, figure shows two resistors connected in series with a cell of EMF 1.5 and internal resistance 0.28. One of the resistors has resistance 1 ohm, the other has resistance R. The terminal PD across the cell is 1. That is the PD outside the cell is 1.36 volts, which means the PD inside the cell must be the EMF minus 1.36, which we normally call the lost volts. Show that the current I in the circuit is 0.50 amperes. Okay, so we know that the EMF is always equal to the terminal PD terminal PD plus the lost volts, or the PD across the internal resistance. I'll just make substitution. The EMF is 1.50 equals to the terminal PD, which is 1.36, plus the lost volts. The lost volts can be the current times the small internal resistance. So 1.50 minus 1.36 is equal to the current I times the internal resistance, which is 0.28. So I equals to, I think that is 0.14 divided by 0.28, which is 0.50 amperes. Calculate the combined resistance of the two resistors. So we want the combined resistance of those two resistors. I think there are several ways of doing this. One, since I know the total current, I can use the terminal PD to find the total resistance outside. So terminal PD is going to be equal to the current times the external resistance. So which means the external resistance is going to be the terminal PD, which is going to be 1.36 divided by the current, which is 0.50. Let me check this one. 1.36 divided by 0.50, that is 2.72. That's method number one. Method number two, I can find the total resistance and then I subtract. This was method number one. Method number two, total resistance equals the EMF over the total current, which will be 1.5. Total current is 0.5, which is 3.0 ohms. That is total resistance. Then it means resistance, external resistance is going to be 3.0 minus the internal resistance, which is 0.28. And I think the answer is the same, 2.72 ohms. That's method number two. I think those are enough methods. Then use your answer in A, Roman 2 to determine the resistance R. Okay, so if I have the external total resistance as 2.7, we just subtract. So R is going to simply be 2.72 minus 1.0, which is 1.72 ohms. The circuit in the figure is disconnected and two resistors are connected to the cell now in parallel with each other. On the figure, complete the circuit diagram to show this arrangement. So I have to draw two resistors in parallel with each other. Then these are connected in parallel with the circuit. So I'll just join here the circuit. This was 1.0 ohms and this is now 1.72 ohms. Explain without calculation whether the terminal PD across the cell is now less than, equal to, or greater than 1.36 volts. So remember, in parallel, total resistance decreases. So total resistance has gone down. Because total resistance has gone down, and we know that current equals the EMF divided by total resistance. Total resistance has gone down, it means the current has increased. If the current increases, remember the lost volts, the PD across the internal resistance, which I'm calling the lost volts, is equal to I times the internal resistance. The internal resistance has not changed, but the current has increased. So the lost volts, because the current has increased, the lost volts increases. The lost volts has increased. Remember, the EMF equals the terminal PD plus the lost volts. So that means the terminal PD is equal to the EMF minus the lost volts. But the lost volts have increased. The EMF is a constant, so the terminal PD must be less. So I'll just write now the answer here. And I say the external resistance is now smaller because they are now in parallel. External resistance is now smaller, so the current is greater. So the current is, let's say the current in the cell or the current in the battery. The current in the cell is now greater or is greater, causing a greater PD across the internal resistance, which is the lost volts, causing a greater lost volts or a greater PD across internal what? Across the internal resistance. So the terminal PD is less. I think that is the end of paper 2.1. See you in paper 2.2. You can download the papers on our website freely. The papers can be downloaded for free. Please support us. You can create an account if you want. However, if you want to purchase the notes, you must have an account which is free, but you'll pay via PayPal. Even if you don't have a PayPal account, you can still purchase using your Visa card. Until next time, IBM is saying bye-bye.